calculate the amperage in a 120/240 delta system with a center tap, we will break down the three-phase and single-phase load calculations. The three-phase load is 80 kVA per phase for phases A, B, and C. The single-phase load is 34 kVA for phase A and 41 kVA for phase C. Firstly, we will calculate the three-phase load amperage. Given a per-phase load of 80 kVA and a system voltage of 240 volts, the per-phase amperage is calculated as 80 kVA divided by the square root of 3 multiplied by 240 volts. This results in 230.94 amps per phase. Secondly, we calculate the single-phase load amperage for phase A. With a load of 34 kVA and a system voltage of 240 volts, the single-phase amperage is 34 kVA divided by 240 volts, which equals 141.67 amps. Thirdly, we calculate the single-phase load amperage for phase C. With a load of 41 kVA and a system voltage of 240 volts, the single-phase amperage is 41 kVA divided by 240 volts, resulting in 170.83 amps. Now, let's determine the appropriate panel amp rating. Firstly, we calculate the total three-phase load current. Since each of the three phases carries 230.94 amps, the total three-phase load current is 230.94 amps multiplied by 3, which equals 692.82 amps. Secondly, we consider the single-phase load current for phase A, which is 141.67 amps. Thirdly, we consider the single-phase load current for phase C, which is 170.83 amps. Fourthly, to determine the maximum panel amperage, we add the total three-phase load current to the higher of the two single-phase load currents. In this case, we add 692.82 amps to 170.83 amps. This calculation yields a panel amp rating of 863.65 amps. Based on this calculation, an 800 amp main breaker would be appropriate. It is recommended to select a panel with a slightly higher amp rating to provide headroom for future expansion or load changes. When dealing with electrical calculations, always consult the National Electrical Code, NEC, and local regulations for specific requirements. Remember that working with electrical systems can be dangerous, and it is essential to consult with a qualified electrician for any electrical work. For three-phase power calculations, the formula to find the apparent power in kVA is the square root of 3 multiplied by the voltage in volts multiplied by the current in amps, all divided by 1000. This can be rearranged to solve for the current. To find the current in amps, you would take the apparent power in kVA, multiply it by 1000, and divide by the square root of 3 multiplied by the voltage in volts. For single-phase power calculations, the formula to find the apparent power in kVA is the voltage in volts multiplied by the current in amps, all divided by 1000. Similarly, this can be rearranged to solve for the current. To find the current in amps, you would take the apparent power in kVA, multiply it by 1000, and divide by the voltage in volts. When selecting a panel size, it's crucial to consider future load growth. Overloading a panel can lead to overheating, trip breakers, and potentially dangerous situations. Therefore, it is prudent to choose a panel with a capacity that exceeds your current needs. Some common panel sizes include 100 amps, 200 amps, 400 amps, 600 amps, 800 amps, 1200 amps, 1600 amps, 2000 amps, 2500 amps, 3000 amps, 4000 amps, and even larger depending on the application. The size of the panel you choose will depend on the total calculated load and any anticipated future load increases. When calculating the total load, it is important to consider all connected devices and equipment, including lighting, HVAC systems, appliances, and any other electrical loads. Each of these loads will draw a certain amount of current, and it's essential to account for all of them to ensure that the panel is adequately sized. Furthermore, it's crucial to consider the demand factors for different types of loads. Demand factors are used to account for the fact that not all loads will be operating at their maximum capacity simultaneously. For example, lighting loads may have a demand factor of 100%, meaning that they are always assumed to be operating at their full capacity. However, HVAC systems may have a lower demand factor, as they may not always be running at their maximum output. The NEC provides tables that list the demand factors for various types of loads. These tables can be used to more accurately calculate the total load in the panel. In addition to the demand factors, it's also important to consider the continuous load requirements. A continuous load is defined as a load that operates for 3 hours or more at a time. The NEC requires that the branch circuit supplying a continuous load be rated for at least 125% of the continuous load current. This is to prevent overheating and ensure the safety of the electrical system. Once you have calculated the total load, taking into account the demand factors and continuous load requirements, you can then select the appropriate panel size. As mentioned earlier, it's generally recommended to choose a panel with a capacity that exceeds your current needs to allow for future load growth. In the specific scenario described, the calculated panel amp rating is 863.65 amps. Therefore, an 800 amp main breaker may seem appropriate. However, it's important to consider the availability of 800 amp panels and the potential for future load growth. If an 800 amp panel is readily available and there is no anticipated future load growth, then it may be a suitable choice. However, if an 800 amp panel is difficult to obtain or there is a possibility of future load increases, then it may be more prudent to select a larger panel, such as a 1200 amp panel. A 1200 amp panel will provide ample headroom for future expansion and ensure that the electrical system is not overloaded. Ultimately, the decision of which panel size to choose will depend on a variety of factors, including the calculated load, the potential for future load growth, the availability of different panel sizes, and the specific requirements of the installation. It's always best to consult with a qualified electrician to ensure that the correct panel size is selected. In addition to the panel size, it's also important to consider the number of circuit breakers that will be needed. The number of circuit breakers will depend on the number of circuits that are required to supply the various loads. Each circuit breaker should be sized appropriately for the load that it is supplying. The NEC provides guidelines for sizing circuit breakers to protect against overcurrents and short circuits. It's essential to follow these guidelines to ensure the safety of the electrical system. When selecting circuit breakers, it's also important to consider the interrupting rating. The interrupting rating is the maximum amount of current that a circuit breaker can safely interrupt. The circuit breaker's interrupting rating must be greater than the available fault current at the point of installation. The available fault current is the amount of current that would flow during a short circuit. It's essential to calculate the available fault current to ensure that the circuit breakers have an adequate interrupting rating. In addition to the panel size and circuit breakers, it's also important to consider the wiring that will be used to connect the various loads to the panel. The wiring must be sized appropriately for the load that it is supplying. The NEC provides tables that list the ampacity of various types of wires. The ampacity is the maximum amount of current that a wire can safely carry. It's essential to choose wires with an ampacity that is greater than the load current to prevent overheating and ensure the safety of the electrical system. When selecting wires, it's also important to consider the voltage drop. Voltage drop is the decrease in voltage that occurs along a wire due to its resistance. Excessive voltage drop can cause equipment to malfunction and can also lead to overheating. The NEC provides guidelines for limiting voltage drop. It's essential to follow these guidelines to ensure that the voltage drop is within acceptable limits. In addition to the panel, circuit breakers, and wiring, it's also important to consider the grounding system. The grounding system is used to provide a path for fault current to flow back to the source. A properly installed grounding system can help to prevent electrical shock and can also help to protect equipment from damage. The NEC provides detailed requirements for grounding systems. It's essential to follow these requirements to ensure that the grounding system is properly installed. When working with electrical systems, it's always important to follow safe work practices. Always to energize circuits before working on them. Use appropriate personal protective equipment, such as gloves and safety glasses. If you are not qualified to work on electrical systems, then hire a qualified electrician to do the work. Electricity can be dangerous, and it's important to take the necessary precautions to protect yourself from harm. Understanding the calculation of amperage and panel sizing for a 120/240 delta system involves careful consideration of both three-phase and single-phase loads, adherence to NEC guidelines, and a focus on safety. By following these principles, you can ensure a safe and reliable electrical installation. Always consult with a qualified electrician for any electrical work to guarantee compliance with local codes and regulations.